y equals, we have option 1, that should be set to our scatter plot. All right, we don't want the residual plot on just yet. All right, so zoom 9, once you have that set up, and you have the graph. Now, this graph shows that we have some outliers. All right, we have one that's kind of off the beaten path in the vertical direction and one that's off the beaten path in the horizontal direction. All right, an outlier is anything that's off the beaten path, but if it's off the path horizontally, we call that an influential point. So we have a point over here in this neighborhood, whatever this one is. I can hit trace to get that particular value, if I can ever get there. Let's see here. Does not want to go. All right, well, sometimes you got to just kind of go back left and right. Okay, yeah, 2040. I mean, you could have just read it from the table, but it's that point. All right, that one is the, if we can get the data to back it up, that's the one that we would call the influential point. All right, and I'll show you that in a second. But when it comes to creating the graph, that part is easy. But analyzing the graph is a different story, because you kind of look at it and say, well, it has one pattern if we leave the outlier and influential point in there. It has another pattern if you take them out. Right? I mean, if I take this point out, it's definitely more linear. If I leave it in, I mean, you could still call it a linear relationship, but the line is going to get pulled towards that influential point. So the line isn't going to fit the data as well as it would if that point was not there. But also, you may look at it and say, well, I don't want to use a linear function. I want to use a cubic function. You know, so a lot of different possibilities. The limit to which is just related to your knowledge of different types of functions. All right? So whatever function you can think of is something that would be fair game. All right? You're not just limited. You see stat, calc. You have all these different kind of regs here. Linear regression, quadratic regression, cubic, quartic, and so on. These are great functions, but you're not limited to those. All right? Any kind of function you can think of, we could actually model using. All right. So let me just go back to the graph. I would want to get this on paper, labeled up. I mean, as far as the sketch is concerned, it wouldn't be too. I mean, I wouldn't put too much effort into it. You're able to use Desmos, so that would be pretty straightforward right there. But yeah, what we need is a correlation coefficient. So I'll just paste this in there later on. But you know, like I said, the digital graph is perfectly fine. All right. Does the data appear to be positively correlated, negatively correlated? It looks like it has a positive correlation. The strength of which is dependent on whether or not we can remove this point. All right, and the context will allow us to make that determination later. All right. Which one is your response and which one is your explanatory variable? Explanatory is the input. Response is your output. Export. All right. So an employer gives an aptitude test to his employees and compares it with their productivity at work. All right. The results are given below. So it sounds like one is, we're trying to use one as a predictor of the other. It's generally what we mean by aptitude anyway. Your ability to perform certain tasks, you know, like whatever the area of expertise happens to be. All right. So we're looking at the score as your explanatory variable and your productivity as the response variable. All right. And then that in conjunction with the graph will get you where you need to go. So the idea here is that if we come up with a linear model or any kind of model, we can use that to make a prediction of productivity based on aptitude score. All right, so correlation coefficient R, let's get out of here, stat calc 8, L1, L2, alpha trace y1 or vars y vars function y1. So we have an R value of 0.444, right? Does it support your answer to part A? Well, it's positively correlated. Well, the positive part, yeah. I mean, the strength of the correlation is suspect, but it does support the positive correlation. All right. Doesn't talk or really give us any sense of strength. I mean, it gives me an idea that, all right, based off the scatter plot, that there could be a strong relationship, but it all depends on that influential point, whether we're allowed to remove it. All right. The regression equation, y hat is equal to 25.844 plus 1.546x. All right. It appears that we have an outlier. Now, when you run the regression, it plots the line, and you can see it's not the best fit ever. So we're looking at an outlier on the high side. I accidentally hit that button. This looks like an outlier. It's a little off the path, but on the high side. All right, so I'd want to know what that point is. All right, you could get it from the data. I mean, it's most likely the one with the highest y value. All right, and by most likely, I mean definitely. All right, 'cause it's the highest one. All right, so 870 looks like it. But if you're not sure, hit trace and go back and forth until you get there. 870. All right, so it appears that we have an outlier 870 and an influential point at 2040. All right, so what we do is we remove the potential influential points from your graph, from the data set from the graph, and then recalculate the regression equation. All right, so the way I handle that stat edit is I first make a copy of my L1, L2 into L3, L4. So enter L1 on L3, enter L2. All right, so I have my data in its original form. I don't have to worry about retyping it in after I make some edits here. All right. So 2040 I'm going to remove. So I go down to the 20, I hit delete. Go over to the 40, hit delete. Make sure that I have an equal number of entries in L1 and L2. And then run the regression again. Because if I just go to the graph, it'll remove the influential point, which will be great, but it's still going to have the old regression equation. All right. So stat calc 8. You can do it this way, or can look for previous calculations that might already be there. I still have that 0 there. I don't know why I had that. But if you just go into the history, you can pull up a previous calculation and not have to type in everything again. All right, but now I'm looking at an R value that's much more, well, we call it significant, but without really having a true understanding of what that means till we get to the next unit, it's a better R value. It's closer to 1. All right, we'll look at the picture in a second. All right, so we have an R value of 0.785. Y hat would now be 2.3-ish. If we go to 3 significant, it would just be 2.300 plus 5.0985 x. All right. So I'm looking at a slope value that jumped dramatically. All right. It went from 1.546 to 5 and change. All right. Now, according to the picture, we're looking at something that's a better fit anyway. All right. That outlier is still a little troublesome. All right. But it doesn't look like it's impacting the fit as much as the influential point did. In fact, what we can do is we can just do a quick comparison. So stat edit. I'll just bring back my original data set. Run the regression without the 870 in there. See what happens there. Because that's not an influential point, it's just an outlier, but I'll leave the influential point in there. All right, so run the regression again, and you see that there's no real marked difference in the slope. All right, slope is pretty much the same. It went from 1.546 to 1.59. Y-intercept didn't really change a whole heck of a lot either. Although it did change, it didn't change a whole heck of a lot. All right, but the slope, when you remove an influential point, changes dramatically. Now, if I take a look at the picture here, it's still not that good of a fit to the overall bulk of the data. All right, it was the removal of the influential point that had the biggest impact on things. All right, so that vertical deviant wasn't that bad. All right, it's the horizontal one that was the problem. All right, so stat edit. I'll just overwrite. So this is 870. Bring that back. You know, you just find yourself second entering a lot, running a calculation over and over again in order to get the job done. It doesn't feel perfect, but I think it's right. So anyway, the residual plot tells us the appropriateness of a linear regression model, right? So that's an important thing because we just did all this stuff. How do we know it was appropriate to go down a linear path to begin with, right? So it's just a question of, are we doing the residual plot with or without the influential point? And that question is always going to be a question. It depends on the situation. So we go back to the original framework of the problem. An employer gives an aptitude test to his employees and compares it with their productivity at work. All right. So I'm looking at the 870 and I'm looking at the 2040. All right. But it's really, again, more about the 2040 because that's the influential point. So my question would be, is that a point that shouldn't be there? All right. If it's a valid result or outcome, then we can't take it out. But if it's the result of a mistake or some flaw in the study, so mistake as in a data entry mistake, flaw in the study as in there's some weird outcome that could be present in the study that the designer did not take into account when they implemented it. All right. So it's kind of like you take a test in a class, and like they're all multiple choice questions. The teacher didn't intend to have two correct answers for one multiple choice question. It accidentally worked its way in there. That's a flaw in the design of it. All right. It would be the other way around. It would be if you got the question right and the teacher accidentally marked it wrong. All right, one is just more of a physical error. All right, so in this case, aptitude test, the individual got a 20, but yet they didn't perform very well at work. I mean, just think about any instance in life where you might be tested and yet the results of that test may not translate to a practical application. The first thing I think of is getting your driver's license. You take a written test. I mean, I haven't done that in a while, but you have to pass it, right? There's no choice. Like if you fail it, you can't get a license, right? You have to pass the written test.
I feel like a 75.
75. All right, so you got to get, okay, so 75. And then you got to do another aptitude test, the road test, right? You got to do some studying in there, like you still do that 5-hour course? Is that a thing? Yeah. So then you do all that stuff. So now you're extremely qualified to go out driving. And yet there's accidents all over the road all the time. Right? So does one necessarily lead to the other? So performing well on an assessment, does that necessarily translate to success in the field? Not necessarily. All right. And because we could say not necessarily, it is possible that an individual did very well on the assessment and it just doesn't translate to productivity. All right. That's a possibility. The other one is actually more suspicious, but since it doesn't impact the outcome of the regression, we would leave it anyway. But that 870, I would look at that as more of a flaw in the design, because I'm just kind of imagining the boss coming in and saying, all right, we're going to take a test today. And then an individual who's a really good worker has been working here. I've been working here for 40 years. I don't need to take a test. So they take the test and they're like, yeah, whatever. Choice C, choice B, choice blah, 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 blah. They mail it in. They're like, what does this matter? I know what you're doing. I'm a good worker. I don't need to pass this test to demonstrate that. So somebody who didn't take it seriously, and yet they're still a good worker. I mean, that happens all the time, right? So it's possible that you could have that outcome where a person is just a poor test taker. So we still leave it in there, but it's also, I'd say, just as likely that a person is like, forget this thing. I'm not even going to take it seriously.
I was just going to ask, so then would you keep it?
You still keep it because it could happen. That's the thing. If it can happen, you got to account for it. So what that means is we go back to our original data set. So I'm just overwriting L1 with my L3. Just saves me from having to think. I know that I had all the original data in L3 and L4, and if I just overwrite it in there, I'm not going to have to go through and be like, oh, did I make sure to put back what I took out? But then you just got to remember, run the regression again. So I'll just do it from top to bottom here. Stat, calc, 8, L1, L2, alpha, trace, Y1, little muscle memory there. You get your values, all right? Then to get the residual plot, we go into, now if you set this up, when I asked it to you yesterday, then all you would have to do is hit enter on this equal sign to turn the regression equation off, enter on plot 1 to turn plot 1 off, the scatter plot, enter on plot 2 to turn the residual plot on. All right. If you didn't set it up yesterday, again, this is how you do it. So second, y equals? A calculator? Yeah, bottom left-hand drawer over here. So plot 1 should be set up with the scatter plot, all right, L1, L2. So that's, you hit enter on plot 1, you go down, hit enter on the scatter plot, and you make sure it says L1, L2 here, second 1, second 2. All right. The second one, enter on plot 2, make sure it says scatter plot even though we're plotting a residual plot. L1 for your X list, residuals for your Y list. All right. And again, you get that by going into second, stat, and right on down towards the bottom, should be at the very bottom, resid. Resid for residual. All right. So if that's the only one that's on, then you hit zoom 9, and now you have your residual plot. All right. And it's kind of tricky because it is very much in the eye of the beholder. When you create a plot, a residual plot specifically, remember yesterday I said if there's a discernible pattern in the plot, that means a linear model is not appropriate. right, in the residual plot, if there's a discernible pattern, then the linear model is not appropriate. That's what I mean by in the eye of the beholder, because some people can look at it and say, yeah, I don't see a pattern. Good, linear model is the way to go. And then other people will say, hey, you know what, it looks kind of cubic there. You know, you start down over here, you go up, and then come back down. Oh, I see a pattern. So you're both right, right? As long as you have the explanation of, and really it's just the relationship between your answer and the explanation that'll get you full credit or not. So you'd say linear model is appropriate because there's no discernible pattern in a residual plot. Linear model is not appropriate because there is a discernible pattern in the residual plot. Luke?
If you were like explaining the implications as like you couldn't use a residual model, would you just like not construct a residual plot on that thing and just write out your answer that like because of outliers?
You could go the explanation route, yeah, and not actually create a plot. Is that what you're saying?
Yeah, and then how would like just looking at that line, like a T, like how do you just like look at that and like address like plotting points or just?
Oh, here?
Yeah.
Oh, just because it says it. Yeah, it's just telling you to construct a residual plot. So this is your x and y axis. Yeah. So, yeah, you would just pull. I mean, if you needed to, and just to do a rough sketch, you could just kind of pull it right off of here and say, 1, 2, 3, tick marks, and just kind of count it off and just kind of eyeball it. But that's what I was saying before. Just go with either Desmos or or just like a picture of it, I guess.
In your explanation, if you're like arguing for a residual plot, instead of drawing it, could you just like show the correlation coefficient and like explain that it's a strong correlation?
Well, that's the thing. You can have a strong correlation where a linear regression might not be the best approach. Because you could have, if you have points that are arranged like this.
Mm-hmm.
But it's like close to the axis, then it could still have like a high R, but not be.
Yeah. You could have a very high R out of this.
It's like super close to that.
Exactly. But then, I mean, I'd look at this and say, well, there's definitely a curve there.
Yeah.
So that's the thing. That's why we get into the residual plot. Linear model is not appropriate because there is a pattern in the residual plot. Right. And like I said, I'll just pop in the images later, but that's really what it comes down to. All right, whether or not you see a pattern. I mean, just as many people would see a pattern as not see a pattern. You look at this and say, I see no pattern. All right, then write that a linear model is appropriate because there is not a pattern, or there isn't a pattern in the residual plot. All right, so, bottom line is, as long as you know the relationship, you really can't get that one wrong. All right, so when they say proportion of variation in productivity, proportion of variation is the same thing as R squared. R squared actually stands for the proportion or percent of variation. So it's kind of annoying because you're going back and forth between one set of data and another set of data. But if I run the regression with the original data set, so stat, calc, 8, again, alpha trace y1, the R squared would be all I'm looking for, so 0.198. That's including the influential point. Now, removing the influential point, stat, edit, that was the 2040. Instead of going back and forth like this, sometimes like when you have an idea of what the influential point is, you create two sets of data and just run the regression on L1, L2, and then a separate regression on L3, L4, just so you don't have to worry about going back and forth, taking data points out, putting data points back in. All right. So 0.617 would be my R squared in this situation, all right, without the influential point in there. All right. We actually move towards using R squared as more of a basis of evaluation of strength of correlation than we do for with correlation coefficients, because it's more flexible for other types of functions. All right. So the closer the R squared value is to 1, the closer it is to a perfect fit, but it also will work for cubic functions, trig functions, whatever kind of function. All right. So in H, it says new job, applicant scores a 9 on the aptitude test. The employer wants to predict his productivity level, help the employer using the regression without the influential point. It's like one of those, all right, thank goodness, because I didn't want to have to put the point back in. So we're using our y hat here of 2.300 plus 5.0985x. I'm looking for y hat of 9. That was the explanatory response part of it. The input is the 9. The output is whatever we get when we run the 9 through the equation. But the better way of doing this, because this whole equation is stored into y1, is by selecting alpha trace y1, open parentheses 9, close it up. That's function notation. That's the same as saying f of x, or f of 9 in this case. We get 48.187. So the productivity level would be about a 48, 49 for this individual. All right. So depending on how confident and we'll talk about confidence in the next unit, but depending on how confident the manager, whatever it was, employer is in the relationship between the two variables, this may be a determining factor of whether this individual gets the job. Because if another person scored a 12 on the aptitude test and the employer is very confident about the relationship between aptitude and productivity, then the higher the aptitude, the more the productivity, the decision would be pretty clear. All right. Now, just very quickly, I wanted to kind of go over the Desmos approach to this. It's kind of annoying in that you sort of have to go through the process of just typing it all in again, the data, but I'm just going to give you the short version of it. I'm not even going to work with this data set. I just wanted to show you how you determine correlation on Desmos. All right, so you'd hit the plus sign and pop in a table, because tomorrow we're going to do a lot with Desmos. All right, I'm just going to put in a dummy set of variables. Sorry, I already have the variables. I mean data set. So 1, let's say 2, I'll put in a 5, a 9, and a 13. I don't know, whatever. Doesn't matter. And then we'll say 14, 15, 12, 17, 21. All right, do a little pinch zoom to show the scatter plot. Automatically plots it, which is nice. All right, so you don't have to do anything special there. The thing about Desmos that's actually really nice is if you know the structure of a function, you can perform the regression. All right, the only thing is that you have to refer to the variables in the table rather than just x and y. So I know, for example, a linear function is in the form of, well, we're using in the calculator a plus bx. So that's what we would use here. But you might say y equals mx plus b, but I'm going to say y equals a plus bx. All right, so what I would do is type in y1, because that's the y column is y1 in Desmos, tilde. So if you go into the little keyboard here, you'll see a little tilde. That tilde is Desmos' way of saying regresses to. All right, so the y1 regresses to whatever the explanatory variables relationship is in the form of a linear function. So then I would type in a plus b x1, because that's the x column. All right. So it'll give me the r squared value, just by knowing the type of function, right? So the only thing, I mean, really, if you know the structure of a function, like most people know, parabolas could be written as ax squared plus bx plus c. I mean, you've been doing that for years. So if you wanted to regress to a parabola, you use y1 instead of y, you use x1 instead of x, and you use a tilde instead of an equal sign. All right, so as long as you know the structure of the equation you're looking for, make those little adjustments and you're good. Gives you the r squared, gives you the r, gives you the a, gives you the b, and if you tap on this little button here, it'll give you the residual plot. You can turn off all this stuff and just look at the residual plot. It creates a column in the table with just the residual values. It's like one-stop shopping, right? So, I mean, but the thing is, you kind of sort of have to learn the language of Desmos, which is it's kind of annoying, but there's a payoff to it, all right? Because that, I mean, we just did like 2 pages worth of stuff. I mean, it's a different data set, of course, but like 2 pages worth of material just by typing in a few things, right? So, and also with Desmos, you can save it. So, you know, you kind of have a running list of like, or these are my regressions. So all you'd have to do is change your data set. Right? So we'll do more with this tomorrow because I want to get into those different types of functions because it's not just a matter of linear functions, and it's not just a matter of taking those regressions that they have stored in the TI. In fact, those are kind of off limits. When they say, you know, like the quad reg, the cubic reg, and so on, those are not helpful for us. All right, I have other techniques that I'm going to show you, and those are more in line with the AP approach, and they're actually more mathematically sound. All right, so that's what we're going to get into starting tomorrow. All right, so that'll do it.